Well, hi, and thanks for joining me here in my shop. Today I'm going to go another step or two with this radio. So let's just recap on what the situation is. The radio appears to be largely working with low output. So you have to turn the volume very high to hear it. Seems to work on all bands, but again, very weakly. On the AM band, it's definitely able to receive stations. That's not so bad. So it's loaded with all of its original components and parts, and we can guess some of them are not performing as well as we might want. So why the low output? I also tested all the tubes. The output tubes, there's a push-pull output in this receiver. The output tubes seem weak. They're right on the reject point in my tube tester. So if my tube tester had its way, I would replace both those tubes. But of course I'm not going to do that with this radio because of the expense involved. And how do I know really that the low output is because of weak output tubes? I don't know that. And how weak would they really be? Just because they're on the line on one of my tube testers doesn't mean they're necessarily operating that quietly. So tubes could be implicated. But more likely there's components that are implicated in the low output. And I can think of a couple capacitors through which the entire signal is passing, either the RF signal or the audio signal. Those capacitors, if they're not capacitating properly, may block the signal. Another possibility is grid blocking capacitors, those capacitors whose job it is to keep B plus from reaching the grid of a tube. Those guys could be a little leaky, and that leak can vary the grid bias on tubes in the radio, one or more. In particular, the output tubes are a concern in this respect. If the blocking capacitor is leaky, the grid can be pushed positive, and then what you get is really heavy current through the output tubes. I don't think you get any more volume out of it or any less volume out of it. You just get more and more current flowing through those tubes. Now at some point it would become bad enough that there would be distortion and other things, but I didn't notice any particular distortion with this radio. It's just quiet. So how to approach this? Rather than start testing every individual component, I'm not about to do that. I think we can look at the radio in big chunks. So one chunk is, let's call it the radio part, and another chunk is the audio part. And right between them is the volume control and detector circuitry. So at the point of the detector, what you're doing there is you're rectifying the output of the earlier stages, the IF stages in particular. And that produces the Avc voltage, a DC voltage. And that voltage kind of tells you how much is coming out of the IF. If we measure the Avc voltage and we find it with a strong signal going in the radio, we find it up -10 or something like that, that would tell me all the earlier stages of the radio are essentially working. If on the other hand the Avc voltage is only -2 or -3, then I become a lot more suspicious that the weakness in the radio is taking place in the front end. And of course the biggest problem of all in dealing with a weakness in a radio like this is that it may not be weak in any one place in particular. It just may be weak all over the place, and all that adds up to low volume. So as I hunt for a specific cause, there just may not be one. And every little improvement is just that, a little improvement along the way. So I think maybe just in talking about it, the first thing would be, let's check the Avc voltage and see what that tells us, and then we'll go from there. I'm going to have to set the radio up so we can get access to a good spot to test the Avc voltage. I'm going to have to tip the radio up, unfortunately. Okay, let's just check a few things out on the schematic here. First of all, the development of the Avc voltage and where can we connect a meter to look at it. So we want to zoom in on the detector. Here it is here. And so the maximum, what are they doing here? It's only using, so So they're grounding one of the plates here just to get it out of the picture, I believe. So this is running with just one diode plate. Doing the rectification. We could pick off AVC voltage here, anywhere above this resistor, really. And we would get the full shot, so to speak. What the maximum that's coming out of this tube would appear there. If we come down here, look at, they have their own note here. Oscillograph connections, vertical high. So this is the point at which the engineers who designed this are suggesting is a good takeoff point, in this case for your oscillograph or your oscilloscope. But you could certainly put a voltmeter here too, a high impedance voltmeter. When you get on the other side of this large resistor, the situation changes. The impedance of the circuitry is very, very high at this point, and hooking up a voltmeter or something is going to leak too much charge out of this high impedance area. So you don't want to hook your meter up here. Back here would be the place. Now, where is it convenient? Like, where is back here? Back here is just in the radio somewhere. Where? Come down here. So this is the switch that's mounted right up on the push buttons. That's up on top of the radio. That's a fairly accessible point. The shielded wire. This is also shielded wire. It's a little tricky to access this and know what you're doing, but there may be a spot up there. I can get a hold of it. Get a hold of the AVC voltage. Otherwise, I've got to look in the radio and find this spot. We could also test it here. We should probably test it here. You know what? I can probably 22,000 ohms. Oh, why has it got an E there? Huh. And an F there. Oh boy. Looks like there's a chance this resistor is contained inside the can for this coil, along with this capacitor. And that would be a 6-terminal coil. Well, we'll take a look and see. If that's the case, if we can figure out which one's terminal E, that's the terminal. There may just be wires coming out of this, though. We'll have to take a look. Let me take a peek. And the peek is, they're all terminals, so we should be able to track this down. They may even be labeled. Well, that's kind of interesting. Okay, now another whole issue is how is the biasing done on all these tubes? So we can guess that the AVC is driving the bias. So let's follow it back. AVC along this line. So here it goes to the I. Make the I tube work. Come along further. Another big resistor. Go up here to the grid. Okay. Looking for any other input of voltage. There isn't, though. So it's all riding on this on the AVC. Through here, grid. What about the very, very first tube? There is no first tube. This is the first tube, and its grid is controlled. So all these tubes are controlled by the AVC. So we don't have to worry about those. The bias on the triode part of this tube, how they do this exactly, I'm not sure. I can't even figure out what's going on in there. So grid, here we are. 10 meg to ground and a capacitor. So this looks like a grid leak biasing here. I'm not absolutely sure though. But the AVC is not going to operate it's not going to affect the grid on this tube. Not the right kind of tube. Now we come to the output. So here they are. And somewhere in here there has to be a circuit flipping the signal. Here it is here. Phase inverter right there. Phase inverter. Flip over the signal. So the grid here is getting its biasing. What's this? 470. It's definitely the grid. Here's the blocking capacitor that I'm worried about. See, over here is B plus on the plate of this tube, and it's just B plus on this side, and nothing over here, hopefully. Any charge that does leak through, there's always a charge leak rate, always. It would normally be so tiny that even this big 500,000 ohm resistor would drain it all out. But if you can get the flow rate, the leak rate high enough here, then the discharge rate through the resistor will be a little too slow, and you'll start building up more and more positivity here. But what's making this negative in the first place? Am I missing something? Okay, so look at the cathode. Look for a cathode resistor. That's what I'm missing. So follow the cathode. Keep following the cathode. Here's the other cathode. Oh, voila! Here's the cathode resistor here. 470 ohms, bypassed by a big 20 microfarad. So this is what would concern me a lot. It may not be operating right. So this resistor may have gone high, or something else may have happened to it. This capacitor may not be capacitating anymore. That would cause grid bias problems and maybe quiet the output here. It's a bit of a silent killer. Now what about signal passing capacitors? So here's one here. So this guy is, all the audio that you hear is going through this capacitor. So if this capacitor is bad, maybe it's not going through. Now it says it's a 0025 a C29. I think there's a parts list here. Let's look at what kind of part this is. C29. Don't they have the numbers on here? C29. Here we are at the back here. Let's look at the back. Okay, C20. There's C29. Well, it doesn't say anything about it. Chances are this is a ceramic or mica type capacitor, and it's highly reliable. Maybe not. We should go looking for this right away. Okay, we can do that. Let's look for it and know where it is. So it was 29. C29. C29, somewhere near the output tubes. Somewhere near... Hold on. Look at this sideways. Somewhere near the output tubes. Where are you? Output tubes. Hey, who stole the out? Here they are. Output tubes. Looking for C29. I don't know that it's necessarily here on the schematic. Yeah, C30. C29. Oh my gosh. Oh, there it is. C29 shielded on one side. So we're going to the volume control slider. So here's the signal. Wait a minute. What's this? C29? Did I get something mixed up? So this is the capacitor that's blocking the passing the audio. What did I get wrong there? Got myself totally confused. C33. And C29. Oh yeah, C29. Let's look at it again, where it is in the radio, and then I'll look at it in the real radio. That's the whole idea here. C29. C29 is located there, hooked up to this pin 1, 2, pin 2 on the 6SQ7, pin 2, 6SQ7. Okay, let's look at the radio. pin 2 of the 6SQ7. Okay. 6SQ7. And that's going to be, let's see, 6SQ7 is going to be this tube. All these, I think this is the grid blocker right here. This is what I'm looking for, I think. So this will be connected to pin 2. Pin 2 in there. Pin 2, eh? So I'm looking at the bottom of the tube and I'm looking for the key so I can start counting pin numbers. Cannot see the key there. It's really buried under parts. There it is. There it is. Okay, so that's 1, 2, 3. Is that right? 1, 2, 3. This is hooked up to pin 3 and it goes to, well, you know what? They've labeled on that, this is the IF transformer. They've labeled them. They've labeled the terminals. H, I, A, B. So it looks like terminal B. Looks like terminal B on here. Terminal B to number 3. Let's see if this is really the capacitor. Okay, back we go to the schematic here. And we're talking about, not here, but here. And we're looking, we think this is the capacitor. It's supposed to be shielded on one side, and going back to the volume control, that's an easier track to follow. From here, that should give us 29. And that's not what the capacitor I follow went somewhere else. So I didn't find C29. Let's do it from the volume control. That's going to work. Okay, from the volume control, this is it here. You see it going up and catching the center terminal of the volume control, and then coming down into the same tube here. And guess what? Looks like pin 3. So that's pin 2. 1, 2. 2 and 3 look like they're joined. Is that right? 2 and 3 joined. Is that the case on that tube? Pin numbers. Yeah. I like that. Wait a minute. No. 1, 3, and 4. But not 2. 2 should have just a resistor on it. That's the resistor right there. That's what I'm seeing. So this is definitely the capacitor in question. Now, again, what's this capacitor doing? This capacitor is blocking DC from reaching the grids of these tubes. I could change this right now. I could test it, and we'll see that it's probably leaky to some degree, but we won't know if it was really causing a problem unless we test it properly in the radio by measuring the grid voltage. Why don't we do that? This is all about using the radio. You know, as I've said many times, people watch my videos and they think I'm using my head to fix radios. That I'm really doing quite the opposite. I'm using radios to fix my head. So I try to learn stuff as I do this. So I take approaches that might reveal things to me, you know, for my knowledge gaps. Yes, I have knowledge gaps. Okay. And thank God for the knowledge gaps. If you didn't have any knowledge gaps, if you walk around in life thinking you got it all figured out, what a bore. What a bore. No magic in that. Right. So we want to fire up this radio. I can keep the video running. Is there any reason why we can't turn this guy on the way it is? And the answer would be no. I think it's just fine the way it is. Well, we're going to really find out. Volume down. Radio on. Now I have the signal generator running in the background there, but we're not really making much use of it just now. We want to be on the B. We want to be on the A band. We want to listen to AM because we want to reassure ourselves right away the radio is actually working. That didn't reassure anything. I don't really have a antenna connected. Let's do that. Not hearing much. Did I leave some tubes out of the set? No, they're all in there. Am I confused over tone and volume? No, I'm not. Hey, where's the sound from here? What is going on? So the radio is running with 121 volts. I have the dim bulbs in. Okay, something's up here. The light is on the radio. The radio's own light is on. Well, I know there's power in the radio and the transformer's doing something. What's happened here? What's going on? No clicks or anything. I'm frozen solid. First of all, this voltage is surprising. 121. Let me take one light out here. Hardly dropped it. 119, 118. It's like the radio's not drawing power. That stupid thing is going on. Oh, yeah, this stupid thing's going on. Well, this is the rectifier tube. That might be useful if it was put in the radio. Yes, tubes. Man alive, I'm swimming in tubes these days. I've been doing, I'm not in here, trying to get something done. I'm testing my tube stock. So I'm overwhelmed with vacuum tubes. Okay, let's get it in there. Okay, so this time it's going to work. This time the dim bulbs will be a little brighter. This time the voltage here will be a little lower. Let's go back. We're wiring one bulb. Ready? And fire one. Volume's down this time until it warms up. To lift up one part of the speaker over here. Okay, now we're running with 85 volts. Okay, all is normal. Is that enough? It's enough to get something happening. Sure. Okay, so one of the things we want to take a look at, we can even leave it on low supply right now while we're getting ready here, is the voltage grid bias voltage for the output tubes. Two output tubes are right up here. Probably a big yellow large wattage resistor in the back there. It looks to be in perfect shape. Scale over here is we're on the 15 volt scale. I'm going to put on the 50 volt scale. A negative reading will go upscale. On here, switch to DC on the probe. Okay. Now, so I'm just going to guess it's this end of this big resistor. And this thing went the wrong way. Maybe that's the wrong end of the big resistor. So I will check the other end. I have to push my probe right past the 120 volt power switch doing this. So what I'm trying to say is this could be the last thing I ever do in life. The meter didn't move at all that I could see. So we have some suggestion here that the grid is positive on the output tubes, which is a disaster in itself. So let's just double check a few things. Which, I can do it right here. Which tube pin on the output tube is the grid? The grid is pin number 2. Wait a minute, I got the wrong tube here. The grid is not pin 2, it's pin 1, 2, 3, 4, 5. Pin 5 on either output tube should reveal the real grid voltage here. Output tubes up there. Pin 5, 1, 2, 3, 4, 5. So this is it. This is the grid. I didn't see a thing. I saw nothing happen here at all. How can that be? Grid. Nothing whatsoever. Pin 5. 1, 2, 3, 4, 5. Let's try the other tube. Oh, the other tube is just buried under everything here. Can't even get at it. Is it exactly the same pin position? I can't even tell. The two tubes may be installed exactly the same rotation. Maybe not. I can't see enough to find the pin on there. Oh my gosh. The output of the what's going on? I'm not getting any readings on my voltmeter. Let's put this up, make this positive. Let's see what the B plus is in this radio. We find that possibly here or here. Okay, so we're on the 150 scale. That's reading about 70 volts. Let's give the radio full power here. Let's see what happens to that. 70 volts becomes a little under 100. let's try right off of another tube. So I'm gonna just pick a tube where all the pins are exposed. Really aren't any. Just go around. Hear the radio. Hear the radio playing. We'll go around. Oh! Ooh, what happened there? What happened there? Ah, okay, so there was an effect there where I just touched it with the probe and the volume increased. My guess is we're standing here talking, the volume is going down again. Not enough that we can notice it maybe. And in touching this, I removed the charge. Let's try again. We'll see. Let's remove that charge again. Which pin did I touch? I don't know which one it was. Maybe this one? Can't remember. Is it this one? Wow. Okay, now that's much higher. So that's on the 500 volt scale on the meter there. Now we're getting a better look at the B plus here. So that's 210 volts or so. 210. And this is a rectifier tube right here. This would be the spot. This is showing what's really coming out of the power supply now. Almost 350. There's the filter capacitors up here. It's already down on that side. That's the full, and this is probably, so this last one is probably the bypass capacitor for that big resistor. Okay, so if we're reading on the positive side of the bypass capacitor, okay, a reading of 20 volts. So that should show up grid to cathode. Cathode, is it cathode? Ground, I think the cathode grid is probably, I don't know. So I don't dare try to read right in cathode to grid with this meter, because this is grounded really good. So I'm going to get something ungrounded here. Try to determine what the real bias is on the output tubes. To measure the drop across the resistor, the cathode resistor, or try to measure chassis to the grid. The grid was 3. Wasn't it 3? Was it 3? Son of a gun, I can't remember. Okay, let me look. Let's take a quick look here on the grid is 5. 1, 2, 3, 4, 5. 5. 5 is the grid. That was the other number I had in my head. Okay, so well, this can measure negative and positive. It doesn't matter what I guess we'll do this way. And number 5. 1, 2, 3, 4, 5. This is definitely it. 0. That's to the chassis. But we want to read it to the cathode. Cathode on that tube is pin number 8. So between 5 and 8, we should find the real bias. between 5 and 8. Okay, without getting electrocuted. That's 5. Don't rotate now. This is 8. So the real bias is minus 18 volts. Minus 18 volts. So I'm not too much of a concern about the bias being pushed positive on the output tubes after that measurement. The output tubes are 6K6s. 6K6 power pentode. Output stage of radios used as a vertical deflection in television receivers. Moderate power output, relatively small input voltage. So that's its secret. You can get some power out without too much of a grid signal. Tube may be used signaling or push-pull. It's push-pull here. It's important this guy be adequately ventilated, like all power handling tubes. Okay, next thing it says is the typical operation in push-pull. Okay, typical operation in push-pull. Number 1 grid voltage, minus 25. And we were at minus 19. Minus 25. So it's not quite where it could be, but that's not to say there's a problem there. Not at minus 19. So it is possible, though. The bypass capacitor is up in the metal. You know, it's one of these 3-section capacitors. We're looking at it underneath. Judging from a lack of hum in the radio, from the regular part of the power supply, take a guess that capacitor is in great shape and doing its job. I don't think we should concern ourselves with the bias on the output tubes, not at this point. So the other thing was the capacitor that passes the signal completely from so that's this guy here. Okay, so we can verify this one by bypassing it with a better capacitor or a new capacitor. And where it shows the wire coming to here is shielded. Oh, isn't that interesting? It shows you the sensitivity of this. This lead is just bare. This one's covered, but there's nothing shielded. Huh. The noisy end is not this end. The noisy end's down here. Interesting. You can read right on it. 0.0025. We bypass that with another 0.025 or so and see if the volume doesn't. How loud is this right here? It's not that bad, you know. Really. It's very quiet on shortwave. Let's try another band here. So see, just now I got to turn it up full. Yeah, you know, there's a lot of volume there. In fact, you can't turn it off. It's always got volume there. Yeah, you know, I'm chasing a dirty switch. And there's that musical sound that's kind of like a worry sound. That seems to be on a number of bands. Well, I think I'm chasing ghosts here. Seems to be in good shape, volume-wise. Why did I think this thing was so weak with volume? AVC voltage development. We're going to need a signal. Let's go there. I think the antenna may not be switched down here. There we go. I had him. Well, we'll look at AVC just with those noises, and if I have to, I'll feed a signal in to sort that out. So the AVC voltage can be picked up right. Let's say we should start with the terminals of the detector tube itself. That would be, I'm just looking at the schematic here quickly. First of all, which tube is it? It's the. It's going to be. I think it's this tube here. It's probably this one. This tube here. Yeah, that's right. Yeah, this is the detector. This is the inverter, and then you have the two outputs here. So that's the detector tube. So we want to find the detector, the diode plates on that tube. Diode plates on that tube. Going to be pins 1, 2, 3, 4, and 5. Pins 4 and 5. I don't know, it's a little complicated. Maybe a little more complicated than I think. Let's go, take a look. 4 and 5. 1, 2, 3, 4. I'll do that again. 1, 2, 3. Pin 4 has no, I'm on the wrong tube. Let's see, down here. Oh my gosh. Pin 1, 2, 3, 4. 3 and 4 are tied together solid here. I got to put a clip lead on there and clip my meter in place. I think it's right here. Once again, you hear the volume change and then not come back. This time it went down a touch. It didn't come back. These are all indications of charges in places where you don't want charges to be. Watching my meters misbehaving over here. Okay, tune the radio and see if anything happens on the meter. This isn't moving at all. What is wrong with what I did? Okay, so I did something wrong. Let's get this off. Let's try again. Alright, right at the back, starting at this tube. The guy for sure. 1, 2, 3, 4, and 5. It's 4 and 5, not 3 and 4. 4 and 5. It's really 5. 5 is really where we want to go. 4 is grounded out. 5 is the diode plate we're after. 5. Let's 1, 2, 3, 4. There's 5. Okay, 5. And this might quiet the radio. I don't know. We'll see. Also, setting an easier attack would be here. Like, I think this clip leader's unreliable. Let's try another one. That's better. Okay, so my meter's gone reverse here. So now a negative voltage will swing it upscale. We're on the 50 volt scale. Tune the radio. There we are. Now we see AVC. Just on noise. So 50 volt scale, that's 10 volts of AVC voltage. Lots of voltage being developed. And what this tells me is the IF is strong. It's producing a pretty strong signal to go into the detector. So again, lack of volume. I think maybe that was all smoke and mirrors on my part. Doesn't seem to be a lack of volume here. Now, what else could be a big concern? Well, we're listening to the AM band, and that seems to be plenty loud. Let's go on to short wave. Pick this one. We can find anything on here. Probably not. So we're going to hit the radio with the signal generator. There's not going to be anything coming from the actual shortwave radio stations. Okay. Okay, so we're going to be broadcasting my signal generator signal on the antenna too. That's okay. I got a shortwave enthusiast neighbor, maybe he's going to hear my signal generator go sweeping by. So we're somewhere around 1200 on here, AM band, something like that. Let's see. $1200. Wow, I didn't hear anything. 1200, nonsense. That's nonsense. We're on 31. What am I talking about? We're on 31. Whoa. We're up more like 5. There it is. Okay, now we're going to see what kind of AVC a signal like this is developing. Now, this is a moderately strong signal. That's 10 volts. That's the same voltage as produced on the AM band when we were messing around there with weak signals. It would give a heavier signal. It's a whopper. There's a whopper. And we're getting almost 20 volts. We'll go low. Now this would be kind of a weak signal coming in, but you should be able to hear this. It's still activating the AVC a little bit. So weakness in the signal now, and I'm not saying this is really weak, I don't think it is. It's probably an alignment issue. So having not really replaced any parts, just that floppy capacitor that was hanging out, the radio is working really quite well. You have a cracked capacitor here. But to a large degree, a capacitor like this, it's all about the mechanical positions of the plates physically with each other. Like for instance, these capacitors here are wide open. The plates are wide open to the atmosphere and everything. So just seeing a cracked shell on this kind of capacitor, I don't think it necessarily means a disaster is happening. Obviously, the radio is working. I can't see that there's much else to do here except the alignment. I think that's really what is left to do. I'm sort of proven that the radio is working really quite well. I guess one option would be to simply go in after these paper capacitors. There's 3 or 4 of them. Another option would be to remove all the paper capacitors and all these seal-tight molded capacitors, on the basis that general experience with this shows that these capacitors are unreliable. But the specific situation with this radio is not that. Seems to be pretty good. Why don't we do this? We'll do the alignment. I have to do the alignment twice anyway in most of these radios. The first time is kind of a learning effort. Redo the alignment or align the radio properly, and then see how well it's performing, and then decide whether any more should be done to it. I mean, it's kind of interesting having a 70-year-old radio that works really quite well. And how much improvement could you possibly get if you did do these capacitors? Not much. I wouldn't imagine much. Okay, alignment is next. That's what we're up to. Thanks for watching, and the alignment will be tomorrow's project. From here, I have to go put the snow tires on my truck. Oh. Thanks. See you in the next video.